Okay, AI workloads, they're fundamentally changing data center power profiles and I guess in a nutshell, shifting from steady, predictable loads to highly dynamic, burst-driven demand. How's that redefining what reliable power means in this AI era?
Yeah, so with some of the AI workload changes and this dynamic power that comes out of these GPU clusters, it's just adding a new dynamic to the way data centers think about power. So traditionally, reliability was utility always on, and if it wasn't on, a battery, a UPS, and a generator worked perfectly in sync to transfer that load to the generator and not drop it. That still exists for most facilities. They don't want to drop the load, but the dynamic nature of these AI workloads and the electrical spikes or pulses that it creates adds a new reliability concern in that the utilities don't want to be altering their power or fluctuating their power in these rapid demands. And the chips want to be run at peak compute because that's ultimately what the facility was driven for. So it's just a new opportunity to solve and a new way to think about reliable power within a data center.
Okay, in AI dynamic power events, I think they can spike up to sort of 15 times idle loads in milliseconds even. So what are the specific electrical and infrastructure risks do those instantaneous surges create for what we might call a traditional UPS system, which I guess are either built around lead acid or more recently lithium ion chemistries?
Yeah, so these dynamic workloads can change dramatically. They can be 40% up to 150% of that idle load. When the GPUs go to crunch that piece of data, they command an enormous amount of power over that 50 to 100 millisecond interval, and then they spin that workload back down to idle while those GPUs process that calculation. So the frequency and the power changes dramatically depending on the site, the workload, and the way the GPU cluster is designed. But ultimately, AI machine learning workloads create these rapid 50 to 100 millisecond type pulses every second that change the way the entire system needs to be designed. And there's lots of different fixes in the software side and in the way they control those workloads. But for UPSs, for breakers, for cables, for generators, all of those systems really weren't designed to manage these type of workloads. And that's where the opportunity is for energy storage solutions, specifically an immediate power solution, which is that high power, short duration subset of the market. This isn't hours of battery that's needed. This is 50 to 100 milliseconds of battery that is needed where they can discharge into the GPUs, deliver that high rate of power over that short duration, recharge when the GPUs swing down, and prevent the rest of the infrastructure from having to be exposed to this oscillating workload or these harmonics.
Yeah, I was going to sort of get onto that. So GPUs represent a massive capital investment for organizations. So just how critical is it that immediate power response is there to prevent things like brownouts, drop workloads, or even hardware degradation if there are lots of AI power transients?
Yeah, it's getting more expensive. I think the most recent iteration of the NVIDIA rack, I think just was published somewhere in the $6 to $8 million per IT rack type cost. So that is tremendous amount of capital expenditure, and data centers need to run that at peak power. I mean, you're buying a Ferrari, you need to run that as fast as it possibly can. To do that, you need an infrastructure design that is capable of either absorbing or mitigating these dynamic workloads. And that's where ZincFive and immediate power solutions come into play because we can support not only the traditional battery backup that every facility needs, which is that bridge between utility drop and a generator or some long duration storage device, but we now have a second value add we can bring to our customers, which is allowing their AI dynamic workloads to not ripple through the infrastructure.
Yeah, and in terms of that, immediate power solutions is essential, I guess, for protecting the IT loads, which we've discussed, but also preventing, as I think you alluded to, the AI-driven power volatility, either cascading upstream into facility infrastructure or even back to the utility grid. So just, I guess, how important is that again, in terms of making sure there aren't any, shall we say, hiccups in various other parts of the infrastructure.
Yeah, ultimately the buck stops with the utility, right? They're delivering the power to the infrastructure. So what are they capable of? What are their limitations? Well, traditionally, they don't like to alter the amount of power they're sending out over 50 millisecond type intervals, or they physically can't. And so these come through the system as harmonics or distortion, and they can cause problems at the utility and to other people attached to that utility if the scale is large enough. So when we start talking about gigawatt AI campuses, we're talking about a significant amount of power for that utility, and we're talking about a significant amount of power for this AI workload. And so the utility is ultimately not going to be able to withstand these AI workloads itself. And then the data center customer is required to have these workloads because they need to spin these GPUs and run these GPUs as fast as possible. So somewhere between that chip and that grid, there needs to be energy storage products, and there are being energy storage products deployed to solve this problem. And that's ultimately where ZincFive and the high power, solutions we provide are focused. The industry is kind of the pain points of the industry are intersecting with our strengths. And so that gives a lot of opportunity for us.
Yeah, and that boils down to delivering repeated high power output within milliseconds but that is a significant materials challenge. So perhaps you can tell us how nickel-zinc chemistry provides the high power density, the rapid discharge capability, and cycle life needed for AI environments without maybe the thermal runaway concerns associated with the lithium ion.
Yeah, so really it comes down to the materials in the battery being capable of high power. So that's number one. And then number two is the cycle count. So how often can it do this? And then number three, I would say, is how much energy is it using from the battery to support these pulses? So if we start on the highest power end of the spectrum would be like a super capacitor. Those have very high power output. We have comparable power output, but they don't have very much energy density. So they can support some of these AI workloads, but their battery doesn't have enough gas left in the tank to also provide the battery backup from transferring from utility to generator if there's an outage. On the other side of the spectrum, you have energy storage products like lithium ion, which are very good for many hours of duration, great for that application. But when you put them through high power discharges, they get very hot. And if you cycle these high power discharges, the degradation and the temperature rise gets to a point where the battery can't sustain it. There's safety concerns in general with lithium ion chemistries, but if you're constantly cycling that battery and getting it hot, you're just going to achieve degradation faster or potential safety concerns faster. So for lithium ion, so for lithium ion, they have to dramatically oversize the battery footprint so that they decrease the amount of temperature rise that each cell is exposed to for these cycles, which makes the footprint unmanageable for what data centers are trying to do at the scale that data centers are building. And then somewhere in the middle, you have nickel zinc, where originally starting as an engine start type product is very, very good at high power, short duration. So these AI dynamic workloads do not increase the temperature dramatically over large cycle counts, which leads to very little degradation from the cycle count. We can do this in a very compact footprint because we're very safe. We don't have any thermal limits or thermal runaway concerns. And then we're only using a very fraction of our energy density to support these workloads. So even though we're a high power, immediate power solution, we do have energy density that's comparable to lithium. So the customer can utilize our BC2AI, for example, to mitigate this dynamic workload with still enough gas left in the tank to bridge that gap between utility and long duration if there's an outage.
Okay, and just following up on the safety thing, I mean, rack densities, power densities are climbing significantly. I guess, therefore, the safety margins are shrinking. So, just how important, I know you've already touched on it, perhaps you want to say a bit more about inherent battery safety, including non-flammable chemistries, in terms of
Yeah.
supporting next generation AI data halls.
Yeah. I want to first say that no battery is safe in that they store electrochemical potential, right? I don't want people thinking that just because it's made of nickel and zinc, it doesn't hold a lot of power and a lot of current. Of course, all batteries hold that electrochemical potential. It's what does that battery do in that worst case scenario? So if you have water intrusion, electrical fire, building fire, something like that, what does the battery chemistry do in that situation? How does it react? Lithium ion chemistries typically go into thermal runaway. They generate their own heat source. They have an exothermic reaction, and their organic electrolyte is extremely flammable. That is the crux of lithium ion in those situations. For nickel zinc, we have a potassium hydroxide based electrolyte. It's not an organic, it's not flammable. Our battery case is not flammable. Nickel and zinc are not flammable as well. So, in these worst case scenarios, we both store electrical potential, but we're going to make sure that the facility is not burning to the ground or burning for many days, like we've seen with some of the lithium ion fires in other parts of the world. So that's what safety means to us, is how does the battery react in this worst case scenario? If you couple that with the increased rack densities, which have gone from 10 to 20 to 30 and are now going straight up to a megawatt, you're going to have batteries closer to those racks, most likely, and you're going to have more concentrations of batteries or higher power products in your facility. So when you start thinking about putting a $6 to $8 million, Rubin NVIDIA rack next to a battery system that, if there's a leak, could make sure that facility burns to the ground, those questions start to crop up. What other solutions are out there? Well, there are non-flammable, inherently safe chemistries that don't burn and don't go into thermal runaway, like nickel zinc, that can solve that problem.
Okay, and also with the the AI the increased densities, etc. I mean, space and efficiency are very much at a premium. They're trying to do more and more in less, or at least the same space. So, be good to understand how you referenced it there earlier. I think the BC2AI battery cabinet, it integrates immediate power response with reliable backup power in a single system. And what impact does that have for the footprint and I guess the system architecture as well?
Absolutely. So space is a premium, and that doesn't matter if you're talking in the rack or you're talking at the UPS or you're talking at the grid, because ultimately it's a real estate business. So all of your real estate needs to be maximized for revenue generating assets, and that's the IT gear. And if you're looking at in-rack battery systems to support AI workloads and other, each space you're taking with a battery is taking away from potential revenue generating equipment. So if you're putting battery systems in a modern facility today, that footprint is getting more and more valuable for the data center operator. And the BC2AI has a reduction of 80% or more, depending on the application, over lithium and lead acid in this dual purpose application. And the nickel zinc chemistry in general, being a ground built, immediate power solution, like this is what we do, we can offer those same benefits from chip to grid.
Okay, and in terms of you said, well, obviously we talked about space being at a premium, and clearly there's a financial angle to all of this AI infrastructure, very capital intensive, and downtime on the other side is extremely costly for organizations. So how does combining immediate response capability with long life cycle performance help reduce the TCO, total cost of ownership, compared to, should we say, traditional dual system approaches?
Yeah, the safety saves a lot of costs. Fire suppression and other concerns that you need to design a facility for, those are huge costs. That footprint we spoke about, if you're reducing your overall battery footprint by 80% or more, you're saving significant money on infrastructure, or you're using that footprint for revenue generating assets, which help tremendously. And then having a chemistry that is a long life, so 15-year life, 10-year warranty, but capable of supporting these workloads, that's going to reduce that TCO significantly. The other interesting thing with the BC2AI is the data center market is primarily built by colocation or hyperscalers that build a facility and the infrastructure, and a tenant comes in, sometimes multi-tenant, sometimes single tenant. And so these data center companies need to design the infrastructure from the UPS to the grid that can support any workload, and specifically an AI workload. They don't necessarily have control of what the IT rack is going to look like. So whether it's going to have capacitors or nickel-zinc batteries or something like that in the rack for these AI workloads, they don't know that and they don't have control of that a lot of times. So what the BC2 AI allows them to do is use a battery system and a UPS for battery backup, which is number one. And it allows them to have a battery system that is capable of supporting these AI workloads if that tenant comes in, is running high power GPU clusters, and those dynamic workloads are rippling through the infrastructure. They're covered. They have a battery that can do it.
Okay, and one other sort of characteristic, if you like, of the AI demand is it's accelerating energy consumption quite significantly. Therefore, the industry is obviously working towards sustainability and net zero targets, but these are, I guess, under pressure. How does ZincFive, I think you report 25 to 50% lower life cycle carbon footprint. I guess that's a major help for operators when they come to scaling AI responsibly, but also trying to meet their ESG commitment.
Yeah, absolutely. Sustainability is in everything we do. It's one of our core values. And I think it is for the bulk of our customers. We did an industry insights report as an example, and 87% of the people that filled out our report said that sustainability was a priority. So it matters to this industry. And what we've done is we've put real numbers behind this. So we have environmental declarations, we have PEP Eco Passport, we've logged that with the European Union as well. We have a full life cycle analysis. So we have the real math and data, peer reviewed behind our claims on sustainability. And what it means is that 40% lower embodied carbon per battery cabinet if you utilize ZincFive versus some of the more common lithium ion batteries on the market. And if we kind of sum up the TCO and the lower footprint and all of those things, that's reducing carbon as well. Less building space, less container length, less battery systems in general. This is really giving customers that sustainability advantage that they need to be thinking about.
Maybe just finally, AI clusters, they're becoming larger, faster, and even more power dense. You mentioned the sort of 1 megawatt rack, which I think everyone's looking forward to seeing when it arrives. And that's particularly, I guess, we've got next generation accelerators. But how do you see
Yeah.
immediate power solutions evolving to support both the hyperscale and the edge AI and maybe, I don't know, other types of critical digital infrastructure?
Yeah, look, I think the pain points of the industry are changing, but all of them are culminating around needing a high power, short duration product. Whether that's the AI workloads we talked about, whether that's battery backup, whether that's black starting generators or turbines. There's so much more opportunity today than there was 5 years ago for a high power battery application. And so what we're really focused on is solving those pain points and talking with our customers and seeing where they're developing. The 1 megawatt rack we talk about, that's probably not going to be deployed in every facility that exists, right? It's going to be a very small subset of the market, although a very large build out when that finally comes to market. But there's going to be a very diverse market space. Not everybody's going to be building a 1 megawatt IT rack facility. Not everyone's going to be building an AI compute cluster. So at ZincFive, we have a wide profile of products, right? We solve all these kind of pain points with one of our solutions, whether it's that high GPU cluster, high compute, high performance compute facility, or whether it's a traditional REIT co-location facility. We have a high power battery that can slot in there and solve those problems.
And just to clarify, will immediate power solutions, do you think at the edge they'll be quite significant there as well when the inferencing happens on a large scale? Because there'll be sort of almost instant requirement for the AI application to fire up, etc. Is that what's going to happen?
I believe so. I mean, I think the AI factories today, there's conversations about whether they even need battery backup in general. They need something to mitigate these dynamic workloads, but if the power goes out, you can pause the training model. And when the power comes back on, maybe you re-engage the training model. On the inference side, They're still going to have some dynamic fluctuations, some dynamic workload that they're going to need to mitigate using, energy storage devices like what ZincFive offers. But the battery backup is going to be more critical than ever because if people are using it and inferencing, right, using these platforms, you don't want to drop that just like Facebook doesn't want to drop customers for an hour. And if you look at the edge facilities, they're closer and closer to populations. They want to be close, right, to users. That footprint concern is going to get even larger. So, how much space do you actually have to put an edge data center? And can you fit a lithium or a lead acid solution? Because it's so big and it's so costly to build that infrastructure with all that safety gear. What does that look like?
Okay, it's been excellent to chat, and thank you so much. I mean, some big, really great insights into what's going on in the AI world. If you like cutting through, there's a lot of hype out there, but you've given us some great sort of facts and figures about what's happening and what will happen in the future. So, Brandon, really appreciate your time. Thanks so much.
Yeah, thanks for having me. I love chatting about it.